Good morning again. Thank you for being here on this third day. All right, so as promised, today I'm going to through Mixed Logit, and I'm going to do the formulation side. I've divided this in two parts. So today is the formulation. It means how you can specify your own Mixed Logit. I have a number of applications because I've been working on this for a long time. And so I want you to understand how to apply this today. Tomorrow I will be discussing about the estimation side because as you will see, this method are much more difficult to estimate, and so they need additional knowledge about estimation. This is the overview of what I'm going to cover today. So first of all, I would like you to understand what are choice probability in Mixed Logit, the two specification of Mixed Logit. You have two different possibilities to specify a Mixed Logit. One is random coefficient that has been widely used in transportation, as I said, in the last 10 years. But there is also another specification, which is the error component that is kind of a nested logit. The fact that Mixed Logit is a very generic model and does not suffer from IIA hypothesis as the logit that we have seen. The fact that under the Mixed Logit, McFadden and Train have tried to unify all the other models, so they see the Mixed Logit as a generalization of all the other models that have been developed so far. How we handle panel data with Mixed Logit, and I will show you in particular the differences between panel data with Probit and panel data with Mixed Logit. And then I have a number of case studies, and I will cover a number of case studies because I want you to see how to work with this Mixed Logit in practice. So Mixed Logit is perhaps the highest flexible model that can be estimated under random utility maximization. As I was, so all this class has been built on the concept that we want to overcome the three major limitations of standard logit. So again, the three main limitations, it's working, okay, thank you. The three main limitations are random taste variation. So Mixed Logit can handle random taste variation, and actually is much more flexible than Probit because you can handle different distribution from normal. So normal is one of the distributions that you can use when you specify a Mixed Logit, but many other distributions are possible. It doesn't suffer from the IIA hypothesis under the hypothesis that you work with the error component specification. I will show you that. And indeed, you can work with panel data because correlation and observed factor over time is possible. You can specify that. As I was saying, the main difference between Mixed Logit and Probit, although there are others, is that you are not restricted to a normal distribution, but you can work with many other distributions. Many people object that Mixed Logit was known from a long time. There are applications in the 80s, especially in application regarding the car ownership modeling. Although, again, very few random parameters were allowed because we didn't know how to solve efficiently integral. So, for example, there are examples with one or two random component, and then the integral was solved with quadrature, or it was kind of Mixed Logit for aggregate data. So you know the difference between aggregate and disaggregate data, right? So we are working here, I'm supposing to work with disaggregate data, so with individual data or with household data. So each of the observation represent an individual. While the earlier application of Mixed Logit, they were with aggregate data. So suppose traffic counts from a zone to another, or total market share of small car with respect to total market share of large car. So it means that when you work with aggregate data, you do the simulation once. While here in Mixed Logit, the way Train and McFadden specify it, you do the simulation for each individual, which is much more computationally expensive. So this is, it's always about choice probability here. So choice probability in mixed logit are, so the probability that n chooses size is the integral of a kind of logit, of a logit formula, right? This is exactly logit, multiplied by a density function and integrated over the vector of the unknown coefficient. Okay, so the difference between logit and mixed logit is that instead of having one constant coefficient to estimate, you know that when you estimate logit, nested logit, what you get is a value for the travel time, a value for the travel cost, a value for all the other socio-demographic variables. Here you don't have one mean value for all the population, but you have a distribution across the population. What does it mean? That in order to know the distribution across the population, and so the random coefficient, you need to estimate a density. So this is the density of the vector of the coefficient. And you need to integrate over this density. So beta can be a vector. It's not just one coefficient. It's a vector of coefficient, right? And f of beta is a density function. Beta is a set of coefficients. You can specify as many random coefficients as you want. And all the rest is the same, right? So similarities and differences with probit. Let's see. So the similarity with probit is that we don't have a closed form for the choice probability, right? So yesterday we saw that we needed to solve integrals. But now, let's see. What's the dimensionality of this integral? So what's the difference between probit and mixed logit? The dimension of the integral. So in probit, the dimension of the integral depends mainly on the number of alternatives, right? Remember that we had to estimate this covariance matrix, and the covariance matrix is a function of the number of alternatives. So remember that I made the calculation on the board, how many of this coefficient of the covariance matrix we can estimate. Here the dimensionality depends on the number of random coefficient of random component that you have in your own model. So you can have one, you can have two. I've seen model with a lot of random component or random coefficient. The other thing is, at the end of the day, this is a mixture of logit. And solving this integral is much easier than solving the integral for probit because this is a smoother function. So it's kind of taking advantage of the property of logit and extending this, right, over random coefficient and random component. So as I was saying, there are two possible specifications here. The first specification that you are going to see is this random coefficient specification, which is probably the most popular one. And you will see why this is the most popular one. It's because mainly we are using mixed logit to represent the variation, the taste variation over people within a certain group. For example, we want to know the taste variation over a certain category of people over travel time, over travel cost. Because once you have the entire distribution of the coefficient for travel time and travel cost, you can have the curve of the distribution of value of time over the population. For example, Jason is not here, but he was using mixed logit to calculate the distribution of value of time for drivers in a highway in the US. Why this? Because people are talking about dynamic pricing. So you charge toll to people depending on the time of day, for example, depending on the congestion that you have on your highway. So you need not just one value for the value of time, but you need a distribution. You need to know when these people are willing to pay small amount or when these people are willing to pay high amount. Or depending also on income, for example. low-income population are expecting to have a lower value of time with respect to people that have high income. And with Mixed Logit, you can have the entire distribution or value of time estimated. So the rest is the same. So this is exactly the same formulation that we have seen so far for random utility maximization model. Okay, so in random coefficient specification, so these beta are random variables, right? So these beta are usually, so you want to estimate this distribution, and depending on the distribution, you need to estimate the parameters of this distribution. For example, if you have a normal, what you want to estimate is the mean and the standard deviation of the normal. The same for the log normal and for all the transformation of the normal. So for example, all the possible distribution that you can estimate. So the first one is the normal, for which you need to estimate the mean and the standard deviation. And then you can have the log normal, you can have the truncated normal, the uniform, the triangular. People have been using the triangular, non-parametric, and so on. And depending on the distribution that you are using for beta, then you need to estimate a number of coefficients necessary, the number of coefficients necessary to identify that distribution. For some distribution is just 2 parameters, but for some other, for example, the non-parametric, it depends on how many control points you have in your distribution, as you will see later. Again, the normal distribution is the easiest to estimate in the estimation sense. When you have a normal distribution, the estimation process is much easier. However, again, you have the same problem that we have seen with probit. It means that normal can assume either signs, right? Positive and negative. So you will have a part of the population, sometimes small, sometimes big, that has positive travel time or travel cost, which is something that is not what we want. In that case, people have been using transformation of normal, and in particular, they have been using log normal and truncated normal. Now, if you use log normal, you will see that the estimation process becomes much more difficult. It's very difficult to estimate a log normal. The other problem is the fat tail. So log normal produce very fat tail for example, on the 2% of the population, and this affects the mean of the value of time that you are calculating. So we are still debating about if log normal are appropriate or not. You will see some example with log normal. Truncated normal are used sometimes because you overcome the problem of positive value for travel time and travel cost by setting these percentages to 0 and estimating the rest of the distribution. Other more flexible, we have been working on non-parametric. For example, I'll show you some of these examples. The problem is that you need to estimate many more coefficients, and you need a lot more of information because recovering, again, the tails of this distribution can be very difficult. But anyway, we are doing this, and so remember, the random coefficient is when you have a random variable for the betas. So beta is not a constant anymore. It's not one value, but it's a distribution for which you want to calculate the parameters of that distribution. So this is Mixed Logit with respect to logit. But there is another way to see Mixed Logit. So this other way is random error component. So the Mixed Logit error component is used when you want to create correlation amongst the utility for different alternatives. So it's exactly, well, it's very similar to a nested logit. That, for example, our example, this was car driver, and this was car passenger, and this was train, right? So suppose that, so we did that with the nested logit, but you can do this also with Mixed Logit. How can you do that? So suppose that so you have to change the specification of your utility, and what happens is that this, suppose now that this is constant, and these are the normal variable in your model. So this is like logit for now. But you have an additional component here, and this additional component is mu is a vector of random terms with zero mean. So mu is like the beta that you have seen before, except that this is the way you specify this mu is different because it's a random terms with zero mean. So if beta was b sigma, this mu is zero. So this is normal, for example. This mu in the error component specification is normal 0 sigma, right? And what about this z? Z is kind of an additional variable that you create and that you specify in each of the utility for which you want to create correlation, right? So what happens here? Oops. All right, so suppose that you want to create a database in order to estimate the error component structure. And suppose that this is car driver, car passenger, this is bus, and this is train. Right, so these are, the column are the alternatives. And suppose that on the row, you have the variable. So for example, this is x1, which is travel time. You have x2, which is travel cost. And suppose that this is the first observation. So now suppose that you want to reproduce this structure here. What you do is that car driver and car passengers, they are under the same nest. It's not really a nest, but in mixed logit, you want an additional error component to create correlation amongst alternatives. So you create a C variable that is common to the that is specified for the alternative that are in the same nest. So you will say that this is, right? So this is a dummy variable that is one for the alternative for which you want to create correlation. And I will call, for example, this Z1, right? So this is create correlation amongst car passengers and car driver, and 0 otherwise, right? So in order to create correlation for the other two alternatives, I create a second variable, Z2, and I will say that is 0 and 0 for the car alternatives, and is 1 for the transit alternative, right? So this nest structure with the two nests can be kind of estimated with a mixed logit with error component that way, right? So instead of having two lambda k, remember yesterday we said, lambda k1 and lambda k2, you have two mu's. You have mu1 and mu2. And these mu1 and mu2 are random variables with 0 mean and some standard deviation. Now, this is not exactly the same specification of nested logit, but does the same, creates correlation somehow. Now, how do you see if this is significant or not? It's from the t-statistic of this standard deviation. If it is significant, then its correlation exists amongst these two alternatives. If it is not different from 0, then get rid of this dummy variable. Well, you can also do, for example, cross-nested logit, right? Because suppose that you want to do this, right? So you estimate something that is like this, right? Car passengers belongs both to the nest of car and to the nest of transit. Or yeah, you can create many nests as you want. The problem is, again, as Ken Train says very well, you can estimate all these random coefficients, but there is at the end, there is a limit of what you can learn from something that is random. Because at the end, you are estimating all these random terms, but you are not really explaining behavior. These are random dummy, are not behavioral, right? Question?
So, when we specify these z variables, do we worry about perfect collinearity? Perfect collinearity when we specify these variables?
Well, you cannot estimate two of these, right? So you cannot estimate another one like this.
Yeah. I mean, will it cause any computational problems?
If you have many of these, yes. And also, you know the thesis from John Walker, she has a number of issues with identification, although I do not agree with all she's saying, but you should check for identification. Although I don't see any identification problem here. I think she mixes identification problem with estimation problem. So I've always troubled reading her dissertation. I mean, yes, if you add many of these error components, it will be a mess to estimate the model. So I suggest really to limit yourself to the necessary one. I've estimated models with from 5 to 10 of random coefficient and random component, but after that is too much. What John Walker is also saying that in her dissertation is that you can have an heteroscedastic model if you add error component to each of the alternatives. It's like estimating as random the alternative specific constant. In that case, you have an heteroscedastic mixed logit. So it means that you have something like that. Suppose that we have 3 alternatives. So if you have the alternative specific constant 2, you add an error component here. You have the alternative specific constant 3, you add another error component. And you have another alternative specific constant here, and you have a full heteroscedastic model. Although here maybe there are some issues in identification, but I send you to the John Walker thesis in order to do that. I've never worked on this, and as I said, I don't fully agree with her.
Can you give us the name of the John? Is the name? You mean the papers you refer to?
Oh, this is a thesis. This is a PhD thesis. Oh. This is her PhD thesis, Walker, John Walker. So this is a PhD, I think, 2001, something like that.
I specify the z variables with the demographic variables of the respondents.
No, z is without, it's just a dummy variable. Yeah. The social demographic are here.
Yeah, can I say that, for example, the male always z here?
No, this is for the alternatives. Everything is, yeah, this is for the correlation amongst alternatives. It's just create correlation among the utility for different alternatives. So the way I see this is that random coefficient is for the social demographic or for the level of service, while the error component is for the alternative. Yeah, this is a good separation in your mind. So random coefficient is for the level of service or interacted with social demographic, and the error component is for the correlation amongst the alternatives. Once you have understood this, you know half of mixed logit. And as I was saying, the third possible way is this heteroscedastic model. Remember heteroscedasticity? It means that you have a different variance component for each of the alternative. And this is what this is doing, right? It makes sense. Although, as I said, we need to be careful with identification. All right. Okay, this is very important. I think this is the basis of mixed logit. So in reality, these z are kind of additional error terms, right? It's like you are adding error term to the error. So instead of having just epsilon and j, which is what you have in the utility always specified, you also have an additional term which is z and j. In reality, it's like adding another error to your utility. And so you can see the random part of the utility as the sum of the mu z plus the epsilon. Okay, so then what you, for standard logit, of course, z is identically 0, while if correlation exists, for example, non-zero component, then what you have to identify is the covariance, right, the W. Random coefficient and error component are formally the same thing. They are all under mixed logit, but the interpretation of them is different. And also what you can do, you can mix the two. So you can have both random coefficient and error component in your specification, although, as I was saying, once you start to have many of these terms, estimation becomes difficult and interpretation sometimes is also difficult. This is the substitution patterns problem. So mixed logit does not exhibit independence from IA hypothesis. But you need to have error component in your structure. So if you have error component in your structure, then a 10% reduction in one alternative does not imply a 10% reduction in each other alternative. And this is because you have these covariance terms here, and you have this P and I that depends also on P and J. So they do not cancel out the denominator when you calculate the ratio of the probability of choosing two alternatives. So no IIA. So this is kind of demonstration of how mixed logit can approximate any random utility model. And in particular, this is the demonstration. Let's see how much do we have here. So this is the demonstration one can train. So suppose that the true model is this one, right? And suppose that alpha follows a distribution f alpha, right? We have a density for the coefficient. So the conditional probability is that I is chosen if the utility of I is greater than the utility of j for each j different than I. So this is normal random utility model. Then the unconditional probability, given that, so if alpha was one term, this was the unconditional probability. Given that here we have a distribution, then the unconditional probability is this one, right? Where we have the integral over the density of alpha. We can approximate the previous probability with an ML by scaling the utility by lambda. This is the scale of the model. Remember, we have seen that many times. So the utility can be scaled to approximate any other model. Then we add an II at the extreme value epsilon and j to obtain a mixed logit. This does not change the model since it changes the utility of each alternative. Remember that if we add a term to each utility, this does not change the model. And then the probability of n choosing I is this, which is exactly a mixed logit, right? If lambda approaches 0, the ML probability P and I approach the true probability Q and I. And this is the probability of mixed logit. So this is a very general model. You can fit any model under this. Panel data. So this is also very important because this is kind of the easiest way I know to handle panel data. And I will show you the difference between the panel data that we have seen estimated with probit and panel data estimated with mixed logit. So what happens in panel data? When we have panel data, we observe a number of choices over a certain period of time. So suppose that we observe an individual over a period of time that is t. So we observe the choice of this individual n for alternative I at time period t1. And then we have y ni t2, y ni t3, and y ni T, T, right? So the probability of observing this sequence of choice is the product of logit formula. So instead of analyzing each of these choices, we observe the sequence. So the probability is the product of this choice probability over time. So the only difference is that instead of calculating this probability once at a time, under this integral, you have a product of choice probability over the entire time period, right? So you see, from T going to 1 from T. These are all the choices observed. So you want to calculate the probability of observing the entire sequence, right? When you do logit, you observe the first one, then you forget about the first one, and then you calculate the probability of the second one. Here, we want to calculate the probability of the entire sequence, right? So my example of me, this week coming here. So you observe myself on Monday, Tuesday, Wednesday, Thursday, and Friday. So instead of calculating the probability that I work on Monday, and then I work on Tuesday, and then I work on Wednesday, you calculate the sequence of the probability that I work on Monday, multiplied the fact that I work on Tuesday, and that I work on Wednesday, and so on. So this is exactly what we are doing here. Instead of having one logit, so this is not anymore one logit and a mixed logit, but it's a product of logit, right? So you see already the difference with probit, because you have a sequence of logit, but you are not exploding the vector of epsilon like yesterday. Remember yesterday I had this huge vector of error that was for individual, alternative, and time period. Here, no. You see that how it's computationally more appealing. The problem is still that when these probabilities are small, multiplying small number by small number, you get very low value of this probability, and you can get into computational issue when you maximize this log likelihood, right? Another thing is that the way at least CAN-train does, we have tried to overcome this, but we have not reached an agreement how to do this. The way CAN-train does is that this beta, they don't vary over a time period. So it means that CAN-train assume that when I work here, my beta for travel time is constant across the week, right? It's because it's always my beta. So that's why he called this individual estimation of travel time, because my sensibility to travel time is assumed to be my sensibility. It won't change from a day to another. This is questionable, but this is the way so the way he specified this is consistent with this assumption. So once you make this assumption, that's how he's doing it, right? So this beta is constant across time period. So the beta on Monday is equal to the beta on Tuesday, the beta on Wednesday, and so on, right? And this has also implication when you estimate the model. Remember that these are estimated with the simulation, so you just draw one value for beta, even if this is in a sequence of logit choice probability. He's saying that you can overcome this by kind of saying that the beta at n at t is the beta of the day before plus another random term. But I haven't seen any results on that. We are trying to work on this, but I haven't seen the results on this. But remember that this is the assumption. So you have a constant beta even when you work with a sequence of choice.
How about the behavioral economics literature? Behavioral economics.
I don't know.
They assume that the utility will be strict to the future. For example, when you want to join a workout plan, you think you can do it. You want to lose your weight, for example. So you think you can do it today. but for tomorrow, utility function changes.
Yes.
Yeah, so they may have some literature in this kind of specification.
Yeah, I always wanted to do something like that. I've done something, but I'm not happy about the way we specified things. But there have been also attempts on. Yeah, I've seen some things, but nothing that was really. Yeah, not in transportation, but in economics. I have to have a look at this. I have a number of case studies to show. Okay, so this is the famous example that Ken Train has on his book, and this is about choice of fishing site. So this is not a transportation example, but he has a survey of people who have a choice amongst fishing sites. So his objective here is to have a mixed logit estimated as a random coefficient. So he just wants to estimate taste variation. And he has almost 1,000 trips taken in Montana so this is stated preference. So you see that each individual gave more than one response. So each gave about 3 responses. So you have a kind of a panel effect here. And he has 59 possible river sites that were identified, so 59 alternatives. So he used Monte Carlo simulation, and he used you will see what does it. So for the estimation, he used Monte Carlo, and he used 1,000 Monte Carlo draws in order to perform this simulation. So he has a number of variables. So he has the fish stock, which is measured in 100 fish per 1,000 feet of river. So you know how many fishes there are there. An aesthetic rating, so if it is beautiful site, if it is a so-so site, and if it is not a nice site. So this is on a scale from 0 to 3, 3 being the highest. Then you add the trip cost, so from home to the site, including, so this includes both the cost and the value of time spent equivalent to cost. So he's converting time into cost. So at the end, he has just cost. You have another indicator saying if the site is listed in a guide. So and probably if this site is listed in the guide, it's quite popular. It attracts more people. That's why he has this variable. The number of campground in the site. So if you can camp there, number of state recreation access area, so the number of access, the number of restricted species at the site, so if there are particular fishes of particular interest, and then the size of the site. So I told you this quiz. Why the log of the size of the site? My American students, they like quizzes. So why the log? We have seen that. Why this?
Because if you add up the utility function, usually.
This is because it's kind of an attraction variable. So you want that you want this model to be independent from the aggregation level. Very good. Okay. So these are the results. Okay. So as you see, he's estimating a lot of random coefficient, right? So out of the 8, he estimates 10. Random coefficient. He doesn't care about identification, and in particular, he's saying that fish stock, aesthetics, and total cost, they can assume just either one value. They can be all just positive or just negative, and in particular, fish stock and aesthetics can be just positive, right? They can assume just positive value because the more fishes, the more you are attracted by this site. And aesthetics, if this site is good looking, then you are attracted by this side. So you expect only positive value from the first two variables. So you expect positive value from the distribution of fish stock and positive value from the distribution of the aesthetics, right? Is this clear? Yes. While you expect just a negative value from cost. That's what I was saying from 3 days, right? Cost is negative, and we expect that this distribution only delivers negative value. So what he's doing is assuming that he estimates, instead of estimating the coefficient, he estimates a log normal transformation of the coefficient. So for the first two, we are fine because log normal is always positive. For the cost, he assumes that it's log normal, but then he changes the sign of the variable in the data set in order to get a negative coefficient. So if you use CAN-train software, and also if you use our software, which is called AMLET, what you need to do is suppose that this is travel cost, right? And suppose that this was $5, this was $2.50, this $3, and this $3.5. So what you do is that in the database, you have this negative. And then you say this is a log normal, and that is what is giving you a negative value. So, and he's also saying that these four, they can be either positive or negative, depending on the taste of the individuals, right? So he can say, well, this can be normal. This can be normal. So what's happening here? So you see that in order to identify normal and log normal, you just need to estimate the mean of the coefficient and the standard deviation of the coefficient. That's what he's doing, right? He's estimating for each of these randomly distributed coefficient two values. The first is the mean, and the second is the standard deviation. And then he has standard error, and I believe that here everything is significant. You will see that here, depending on the value of this standard deviation with respect to the mean, you have a fraction of the population that has positive coefficient, that has positive value for that coefficient or negative. And in particular here, so if you make the calculation, here you have that 68% of the population has positive value for the site to be listed in the guide, while the other 32% have a negative value for this, because it means that if it is listed, it's a very popular site, and if you want some quiet, then for you it's negative. Campground are preferred by half of the population. So these are preferred by half of the population. So you have really half of the population that wants a campground at the site, and half of the population that dislikes campgrounds at the site, and so on. You can also scale everything by cost, especially the first two, because you need to be careful here. When you calculate willingness to pay, you need to be careful about the distribution that you are using. In this case, is quite lucky because the ratio of two log normal is another log normal, and then you can calculate the mean, the median, and so on. When the cost is normal, for example, the ratio of two normals is not a normal. The mean of this distribution is not identified, and you can just calculate the quantile. So there is a paper about that from Train and Hess. But anyway, here, for example, you can calculate willingness to pay to increase the fish stock. So what you get, because you have a ratio between two log normal. So he says that the average willingness to pay to have the fish stocks raised by 100 fish per 1,000 feet of river is estimated at $1.44. So suppose, so this is the willingness to pay. So if you increase the number of fishes of 100 fishes per 1,000 feet of the river, then you are willing to pay $1.44. Right? So that's So if you have more fishes, then you can charge these people that amount of money, and so on. He says you can similarly about $10 is estimated for a site that has an aesthetic rating that is higher by 1. So to go from okay to a very nice site, you can charge them $10 more. And that's the kind of interpretation that you have out of this kind of model, right?
Possible to know, because the estimate result shows the distribution of the parameters. And is it possible to know who located there and who?
No. It's because this is a random distribution. At the end, this is a very good observation, because at the end we are estimating random effect. So before you do that, for example, you see here there are no socioeconomic no socioeconomic variables. So I think before you start to estimate this random coefficient model, try to separate the deterministic the deterministic heterogeneity. It means that you can interact total cost for some social demographic, and then you have different value for willingness to pay. That's what happened when the interaction term. So actually, you know, Professor Ortuzar, he was a stronger supporter of estimating first the deterministic taste variation and then the random taste variation. If you had a paper 5 or 6 years ago reviewed by him, he said, okay, that's very nice mathematically, but what we are learning. And this is exactly the point, and I agree with him. But you know, this is very appealing from the mathematical point of view. It's a very rich problem, and the fact that you have this distribution, it's very nice. And also there are some cases, now that in transportation we almost always know the social demographics, but there are some cases in which you don't know the social demographics, and in order to calculate heterogeneity, the only way is this. For example, we are working in discrete choice modeling for revenue management, and there we have just internet booking data. So we don't know anything about the individual is booking. We just know when he arrived and what he is buying, and where he is going. So we have very limited information. And if you want a revenue management policy that implements different tastes for price, that's the only way you have. Although in transportation, I agree, we have many social demographics, and here there is nothing. We said that this is a very flexible model. It can approximate any other model. And I want you to make the connection between mixed logit and latent classes. Now, latent classes are very popular. I was looking at there is a ISTTT going on in the Netherlands, which is a very famous conference in traffic. But they had a session in discrete choice model, and Michel Berler, who is the author of BioGym, was talking about latent classes. So this is really the subject of the moment. So if you want to publish latent classes, so mixed logit, as I was saying, is very general. So you have integration over a density function. Now, you can see also this integral as a sum. So instead of calculating the integral over the density, you can have a sum here, right, over a finite number of classes of individuals. So instead of calculating the distribution, what you estimate are the beta for the classes and the percentage of people in that class. This is a latent class model, right? So you can see the mixed logit also as a latent class model. And we have also done this for revenue management, and it worked quite well, because instead of estimating the entire distribution, we estimated the coefficient for the classes and who belongs to that classes. Yes?
So we need to specify how many segments.
You needed to specify, you needed to tell him how many classes you want.
So need to try. You're latent, right?
Yes. So this is a. Yeah, so this is the question we always get from the reviewers. We have done some application, and we did it with 2 classes. 2 or 3 classes. After that, first of all, it becomes difficult, the estimation, and then what you are gaining in goodness of fit, it's not that relevant. So we stopped with 2 classes. We were, I have a couple of applications, and we work with 2 classes. For example, for revenue management, we said 1 class is the business class. For example, we don't even know in revenue management if they are traveling for business or for leisure. So depending on the values that we obtained, we said, well, 1 class are the business people who are willing to pay a much higher price, and the other class is the leisure people who don't want to spend much. So otherwise, because latent classes, you don't know who they are, again. So you can estimate a different coefficient, but you cannot say, well, these are the low income, these are, the interpretation is...
But you have a market variable, market share variable.
Yeah, you have a market, you know how many are in this class, but you don't know who they are in reality. You have the variables that helps you to separate the classes, but yeah. For example, we had the departure time or departure day of week to separate the classes. Perhaps I will show you something like that on a Friday. Okay, so I have a number of studies that I've conducted myself and published over the years. When I was in Belgium, I started to work with a data set called MobiDrive, and that was collected in 1999 in 2 cities of Germany, Karlsruhe and Halle. So this was collected by Professor Kai Exhausen in Switzerland, and he was kind enough to give me the entire data set for free. Well, we co-authored a couple of papers on this. So the peculiarity of this data set was that he wanted to observe the variability and rhythm of daily life. So he had a very few number of households. In particular, he had 160 households and about 360 individuals. But each individual was observed during 6 continuous weeks, right? So you had the entire travel diary for each day for 6 weeks. So you have a very big data set, but from a very small number of households and individuals. Now, given that there was a travel diary, so it was a complete travel diary, I wanted to analyze this in an activity-based fashion. So I didn't want to lose any of the information, so I divided, first of all, I organized the trips into tours, right? So you will see that. So let's try today to make the connection between travel survey data and modeling, because before you estimate a mixed logit, you need to organize your data. Where do you get data? Most probably you get data from diary. So if you open MobiDrive or if you open the National Household Travel Survey, what you have is something like this. So you have individual number 1. So this is the individual. These are the trips. These are the origin, the destination, the mode, the purpose, departure time, and arrival time. Right? So individual, trips, origin, destination, mode, purpose, departure time, and arrival time. So you can have more information than that, but this is really the base of your analysis. And in fact, well, let's start from this. So suppose that this is me. Suppose that I'm telling you what I did yesterday. So what I did yesterday, so the first trip of my day was from the hotel to the university, and I walked. Why? Say for, this is walk, this is for work, the purpose. I left my hotel at 9:35, and I arrived at 9:45. Right? Then yesterday I made a second trip, and this was from the university to the restaurant. The purpose was eat out. And again, I walked there. No, it was walk. And the purpose was eat out. And I left the university at 1:15 p.m. and I arrived there at 1:30. Then I made another trip, and this was from the restaurant to the hotel. I walked again, and say the purpose of this is going home, right? I was going home. I left the restaurants at 14:15, and I arrived at my hotel at 14:25. In the evening, I left my hotel, and I went to a restaurant. I walked, and the purpose was eat out again. It was quite late. It was 8:30, and I arrived at the restaurant at 9 because I could not decide where to go. Too much choices here. Then from the restaurant, I went to the hotel, walk again, and this purpose was go back home, and it was 10 o'clock, and I arrived at all right? Okay, so this is the travel diary. Now the peculiarity of Moby Drive is that you have not just me, but all the person in my household. So this is individual 1, but then you have individual 2, 3, and 4, including the children. But also you have me, and this was, yesterday was Tuesday. But then you have me on Wednesday, on Thursday, on Friday, and then for 6 weeks. So you have 42 times this. So you have a lot of information, and also you have information about the variability of my travel patterns across day. All right, so the way I organized this was, first of all, and you realize here that you don't just have information about trips and travel, but you also have information about activity because you can calculate the duration of the activities, right? In particular, my work activity here is from 9:45 to 1:15. How many hours are this? 3.5, right? So my work activity is 3.5, and you can calculate this for every day. Or you can calculate how much time I spend in leisure, how much time I spend in shopping, how much time I spend with my children. And now people are interested in knowing, for example, Dr. Mamasani is working on how much time we are spending with technology, or how much time I'm telecommuting from home. So I organized this, first of all, I divided the population into 2 parts, workers and non-workers. But this doesn't mean that you work or you are unemployed. It means that if you are working the day I observe you, or if you are not working, because the behavior will be very different. And as I was saying, in Europe, this is quite important because there are people who are just working, they are lucky enough to work just 3 days per week, and the rest they enjoy their life. And in the United States we are not there yet, and I believe here you work hard too. But in Europe they are lucky enough to work 3-4 days per week, including my husband. The travel patterns are quite different from day to day. So this is a day in which I worked, so I belong to the workers' daily activity chain. And then I assume that the most important activity for people who are going to work is work. I divide this into tour, right? A tour starts at home and ends at home, or start at work and end at work. So you have home-based tour, or work-based tour. In this case, I just have home-based tour, right? And so I have a first tour here, and I have a second tour here, right? And in particular, this is my commute. So I have a commute tour, and I have what I call an after tour, so something that happens after my commute. And in particular, I have an evening tour. Right? In particular, for this tour, I have two legs. So this is the commute tour. So I have the leg to work, the leg from work, and also I have an additional stop. So I have the two legs, 1, 2, and 3. So these are two legs, but I'm making an additional stop to eat somewhere. So this is a commute tour with two activities, one principal activity and one secondary activity. The same for non-workers, or people who are not going to work on the day I observe them. And for them, what I do is I calculate the activity that has the longest duration. And I say, well, this is the main activity of the day. And then I analyze if there are activities before and after, right? And so by doing this, I don't neglect any of the information that I have in the travel diary. Remember that many of the so some of the four-step models are still just based on commute trips. But if you analyze data from National Household Travel Survey, you will see that commute trips now in Europe and the United States are 1/3 of the trips. So if you just focus yourself on commuting, you are losing 2/3 of the information, or you are not accounted for 2/3 of the trips and of the congestion. Okay, so that's how I was working with my data. And this was quite difficult because there is a lot of data. So this is just the example. So the work tour, you see, these are the descriptive statistics of my data. So I have non-workers and I have the workers. And see, the work tour is just 30%. Right? It's just 1/3 of the entire trips made. And look at this. People who are not going to work, look at how many trips they make. I used to say that the people who don't work, they spend the money of those who are working, so they have time and money available. So what you can see here is that these people, they are free during the day. And so they make a lot of trips in the morning and in the early afternoon. They don't do much in the evening because they have already done everything they needed to do. While the workers, they don't do much in the morning before work because they have scheduling constraints, because they needed to be at work, say, by 8, by 9, so they cannot do much. Probably these activities are done by the other people in the household that are not working. There were very few people who were going out for lunch, but this is country specific. It depends the way you are organized. Because if you see the same data for France, you have a lot of people going out for lunch. In France, lunch is also very important. So these people, so 30% were going to work, but there was a significant amount of people who still were doing other activities after work, about 11%. So these activities are like shopping or going to gym or going to eat out with friends and so on. Mode share, this is Europe. So you see that this is Karlsruhe. So this is they have a very good transportation system. Public transportation system is a very bike-friendly and work-friendly city. So you see that. You have many walking, many biking. You have less than 50% of people in car. And you have a significant amount of people in the public transportation. So yeah, it's a good example of a small and efficient city in Europe. Okay, so these are the variables that I analyzed, and so I had a number of sociodemographics, a number of pattern variable, and the level of service variable. I just had the time and cost. It was difficult because this was calculated afterward, not by the same people, so it was difficult to make this working. And so I calculated, so I estimated a multinomial logit multinomial logit with interaction with social demographic parameters, a mixed logit, and the mixed logit on panel data. You see that, so forget about this. You see that there is a gain, but not much, because so there is a gain in applying the mixed logit, and here you have the same number of parameters. However, there is not much gain in having time and cost specified as a random coefficient, because I've accounted for a lot of deterministic taste variation. So I excluded all the deterministic taste variation, and then I estimated time and cost as a random coefficient. And as you see, the gain is not much, but the gain is a lot when you account for this panel effect, because you have here huge sequences of, you have sequences, actually these are daily. So when you account for correlation across the observation from the same day, you have a lot of correlation. So that's why you have greater rho squared. So you gain a lot by accounting for this correlation. So this is the old fashion to calculate value of time, and I was able to calculate value of time for different purposes. And you see that what I get, an average of 11, this is Deutschmark, 11 Deutschmark per hour. This was in 99, which is consistent with the value given by the European Commission. A low value for the work or education, and much higher value for other purposes. And this is also consistent with what found in other studies. So you have that willingness to pay for purposes like shopping, leisure, and other is higher than willingness to pay when you travel for commute. This is the value of time by socioeconomic characteristic. You see how many interaction variable I have. So I have time interacted with the fact that the household is in a urban location, the age, different ages, the fact that it's a full-time worker, if it is female and part-time, married with children, the number of stops, season ticket, and main car users. So the fact that I have all these variables reduces the random taste variation. Then I calculated the value of time from the distribution, and again, I took advantage of the way I've organized the data, because now I have the value of time for different tour type. So these are for non-workers, and these are for workers. So let's see, let's look at the mean. You see that about 8 here, 20 in the evening, and here you have 13, 15, and very low values in the evening. But also I allowed all this distribution to be normal to see how much of this travel time was found to be positive, or something that is close to 0. And this is because this was a special call from Transportation Research Part A from Professor Pat Mokhtarian, who was saying that our issue is that not all the population has a negative travel time. There are people who enjoy traveling. So what I found, surprisingly, is that when you commute for work, there are 0% of people have a positive value for travel time, right? This is what you expect. But then in the evening, you have 20% of these people who have positive or 0 travel time. They enjoy going out and then traveling. And the same here. I don't know. This is what I found. These are what the numbers are telling. Now the interpretation of this is, you can believe or not. Professor Mokhtarian liked it, and she published it. But this is another way to see the application of this methodology. So these are the distribution. You see, you have distribution, right? These are the distribution of value of time. All right, question on this. Question on the way I organize data. Question on Moby Drive.
Would it be possible to include both socio-economic interaction and in the mixed logit? Because when I see your course, there's only in mixed logit, you can include social recovery in action terms.
Yeah, you can do it, but
It's logical or it makes sense?
it makes sense, yes. My friend Elisabetta Kerke, she does it all the time. So she mixes the two effects. Now what she does is she has the deterministic taste variation, and then the rest, what is left out, is random. I think this makes sense, and she's a good student of Ortuzar. I think this is the right way to do it. Let me ask a question. So if you don't have a travel diary here, how do you estimate any of this model, or which are the sources of data that you can use in order to make this model working? You don't have any travel diary data collected here. You have the National Travel Survey?
Yeah, we only survey the usage of a public transportation.
Oh.
And more choice.
Okay.
It's a yearly survey.
Okay.
But
It's not a diary.
no data,
I
right?
believe.
No panel. Well, but even in the United States, it's not panel data. It's just one day. One day.
Yeah,
Okay.
one day.
So it's the use of public transportation against, yeah, okay. Do you know the market share here, less or minus? How many are cars for commuting, for example?
They're very different for different cities.
Oh,
For
in Taipei, for example?
Taipei, we have about 40 to 45% in using public transportation.
And
maybe 30s using motorcycle, and 20s in use car.
And let me ask also this, because this is, I'm very interested in car ownership. And is the car ownership increasing, the number of people who are getting a car?
Yeah.
Yeah, rapidly?
Not mature, but for motorcycle ownership is growing.
Oh, okay. Okay.
Almost everyone.
As a motorcycle.
I have a motorcycle.
And biking has disappeared, because I believe.
It's very dangerous.
Oh, because it's dangerous. Okay. Oh, okay. So that's. But before it was, instead of motorcycle, was biking.
Yeah.
Okay.
We also promote cycling.
Yes.
In the survey, it's normally survey one people from a household, or you can survey multiple.
Oh no, this is the entire household.
Entire household.
Yes.
So when you model this data, can you do the members in the same family have similar traveling patterns?
Yeah. Yeah, I've tried later work on this. I've accounted for correlation across the week and the individual and the household. But what you see is that once you account, so it's much more significant, the correlation across patterns from the same day, week, and individual, because then the patterns of the household are quite different. It's more about what I concluded from this analysis is that while what you do is similar from day to day and from week to week, but then there is an allocation of a different activity across household. So my travel pattern are very different from the travel pattern of my husband and of my kids. So I think it's better to go into the direction that Chandra Bhatt has taken, so allocating activity to household.
But because the culture in Taiwan is slightly different.
Oh, then it's, yeah.
Yeah, in the United States, you have like 2 cars or 3 cars in a household, but in Taiwan we only have like 1 car.
Yeah.
To our travel
Yeah.
buy other.
Yeah, and then this is also allocation of activity and cars, because if you take the car, then the partner is left without car, and also he or she needs to do the things that are feasible walking. Yeah. So when I was in Europe, we did something like that, allocating activity and cars at the same time, because depending on who is getting the car, then the pattern is different. So there was huge issue a couple of years ago, 3 or 4 years ago, about which is the right distribution that you use for Mixed Logit. So as I was saying, when you estimate a Mixed Logit, what happens is that parametric distribution are a priori specified, and then you estimate the parameters of this distribution, right? Before you start a Mixed Logit, you ask yourself, am I using a normal, am I using an abnormal, am I using a triangular, or some other thing? But you realize that this leads to a number of practical problems. First of all, it is difficult to assess which is the more appropriate analytical distribution. It's a matter of trying and see if they work or not. Unbounded distribution, like normal, they produce value ranges that are difficult to, that have difficulty in behavioral interpretation. And for example, if you use log normal, the effect of this fat tail on mean are huge, and then you ask yourself if this value is reliable or not. I think starting from 2005, 2006, and for about 4 or 5 years, a number of new methods have been proposed. First of all, Train proposed bounded distribution, and which are simple transformation of normals. It's just that you bound at 0 the normal, and then you give a 0 value for a certain percent of the population. So you estimate the normal after 0, and you give a kind of mass at 0 for those who have a very low or positive value of travel time. Or mass point approach, Dong and Koppelman in 2003, they proposed a mass approach. So instead of estimating the distribution, you estimate the quantile of the distribution. Then there are non-parametric approach. Fosgerot was the first one to propose non-parametric technique, but this technique was applied just to binomial choices, and with this technique was not possible to account for repeated observation or panel data. So he was the first one to propose this, but this approach was not quite general. Approach is global sign condition. You know, Henscher likes to impose this condition. So he said, well, let's impose just one sign to the marginal disutility, and then he adopted this Rayleigh distribution for total travel time. So Rayleigh is similar to log normal, but it's easier to estimate. That's why he was proposing this. S. Birler and Pollack, they proposed a discrete mixture of GEV. So again, this was a discrete mixture. It was not a continuous distribution. There are other papers on this, and lately, Train and Wicks, they proposed, instead of estimating travel time and travel cost, they were proposing to estimate directly willingness to pay. So instead of having 2 coefficients to estimate, you estimate a coefficient for willingness to pay. And this is called estimation in willingness to pay space. So there are many takes. There is a vast body of the literature on that. But then the conclusion seemed to be that it is not possible to identify the distribution to use in all situations. The best distribution fit is highly situation dependent. Yeah, this is always in discrete choice modeling. You need to try and guess what is for you and for the policymaker the best distribution. But we said let's try to apply, try to develop a non-parametric approach for mixed logit. So this is again the classical definition of mixed logit. You see that this formulation does not change with respect to what we have seen before, except that since I'm working with a mathematician, he likes to see this as a stochastic programming problem, because the interpretation of this integral is in effect an expectation, right? And so this expectation, you can apply for this mixed logit all the methods developed in stochastic programming. So we have a number of theories developed on that because I was working with this mathematician. So given that we are working with the random variables, you need to draw from distribution. And the easiest way to draw from univariate random continuous variable is to draw from the cumulative distribution distribution function of the uniform. So you draw from a uniform 0, 1. Then if fx is known, then you construct f minus 1. So in reality, this x can be any vector in some functional space, right? Can be parametric or can be also non-parametric. The only constraint that you have here is that both fx and f minus x must be monotonically increasing because we are working with probabilities, right? There is an assumption here, and well, this is the assumption that we make always when we estimate mixed logit. And the assumption is that for now, that all these random variables are not correlated. We work with univariate random variables, but the extension is possible, and in fact we are working on this because we want to apply copula and then take account of the correlation across these variables, right? Because look at time and cost. It's logical that across time and cost there is certain correlation. So you cannot draw independently from travel time and travel costs, but the logical way to do it is to draw from multivariate distribution. But for now, we don't do this, and as long as I know, nobody does it. So this is the extension to multivariate distribution, but we don't do this for now. So the contribution of this paper was saying, instead of working with parametric distribution, so like normal, log normal, triangular, etc., let's adopt one of the methods that are popular in statistics. So if you see all the publications in statistics now, they are always about non-parametric estimation. So we said, let's try to adopt a semi-non-parametric, because at the end of the day, it's not really non-parametric, but it's semi-non-parametric, because you decided the number of points that you want to estimate. And in particular, we assumed a bounded distribution. Remember that the unbounded are difficult because of the people going to minus infinity and plus infinity. So this semi-parametric distribution that we are adopting, that is called B-spline, is bounded. But this is what we wanted. This was one of the reasons that guided our, and this function is based on a number of knot vectors. So you see that you need to calculate many coefficients. It's not now just about mean and standard deviation, but depending on the number of supporting points, then you need to estimate a number of coefficients that are given by this, right? How it works? It works that you establish how many control points you want. For example, you say, I want to estimate the control point at 0, at 1, 25, 50, 75. In this case, you have 5 control points. Depending on these 5 control points, it determines how many of these knot vectors you need. But you can say, well, I want, for example, 0, 1, but I want 10, 20, 30, and you can have a final representation of your distribution. However, the number of coefficients that you are going to estimate increases. For example, if I'm not wrong, when you have these 5 points, you will have, I don't know, between 7 and 10 coefficients to estimate. So it increases a lot the number of coefficients.
So the 5 points include the starting point and the ending point?
Yes. Yeah. The other problem with that, given that the probability must be monotonically increasing, the other thing is that you cannot use unconstrained optimization, but you need to adopt constrained optimization. So there is also a problem in the algorithm of the optimization that you need to use. And that's why we used a trust region method that was, and we used in particular a constraints optimization method in order to deal with this projection in this space in which this monotonically increasing function was true. Now, this is a second application for which I think mixed logit is quite appropriate in transportation. And this is for pricing strategies. So what we did here, there are different ways to price infrastructure, right? And what you can do, for example, is to price lanes in a variable way. So for example, you can divide your highway in order to have express toll lanes or HOT lanes or high occupancy toll lanes. You can have toll on entire roadways. You can have cordon charges, like in London and Stockholm. In order to enter the city center, you charge people with a fee, or you have area-wide charges. What happened in Milan, for example, they have a problem with pollution. So if you want to enter this, the area, a certain area of the center, you need to pay a charge. And in the United States, we are now particularly interested in this first two applications because they have a problem in maintaining the road. It's very expensive to maintain the road. Tolls are very rare. There are no tolls anywhere. I remember when I was in China, there were tolls everywhere. Every time we stopped to pay a toll, it's the same in Italy if you have been driving in Italy. But in the US, everything is for free, and maintaining these roads is very expensive. And the other thing is that some area, for example, the Washington area, suffers from a lot of congestion. So they would like to alleviate this congestion, maybe with HOT or HOV lanes. So in the US, there are a number of examples, State Route 91, San Diego, and now, this is quite old, but now the part of the Beltway is the ring around DC, which covers 3 states, right? Covers Maryland, Virginia, and DC. When I started this, they were thinking about tolling the Beltway, but now the Virginia side, they have a toll. They have express toll lanes, and so you pay either a toll, or if you are 3 in the cars, you pay no toll and you can use the express lane. But on my side, on the Maryland side, nothing has happened yet. So we'll see. So this is what happened in Europe. In Europe, we have more like cordon pricing or congestion pricing. And we have 3 examples. The example in London, they closed the city center, and the fee you pay, it's very expensive. It's like about £10, something like that. What happens is that they reduce the number of people who were entering the city center, but there was a lot of congestion on the public transportation. So what happened is that they were not collecting enough money in order to improve the public transportation. So they were pleased with the reduced number of cars on the streets, but then they had not enough money to subsidize the public transportation. A similar scheme was introduced in Stockholm, and this is a very interesting application. If you have the chance to read that, I attended a presentation from a guy from Stockholm, and it's very interesting because they did this in Northern European fashion. So they had a referendum. So they asked the people. So they had a trial. So they applied the congestion pricing in the city center of Stockholm for 6 months. So they made the people experiencing congestion pricing. And after that, they had a referendum. So they asked the people, would you like us to apply again congestion pricing in your city? And surprisingly, the majority of the population said yes. And now they have congestion pricing. In Stockholm, it's different. They don't apply, it's not very expensive. But it's just the mentality that has changed. People are biking, people are using public transportation, people are buying electric cars, and the results that they got were unbelievable. Like 35% of the pollution disappeared from a day to another, and the use of car decreased by an unbelievable number, 20%, 25%. This is with just one measure. You see that in transportation, in order to have significant results, what the professor tell you in class is that it's very unlikely that with one policy you get results. You need to have a number of policies together. I think the only exception in transportation is congestion pricing. Congestion pricing is the only measure of the difference alone. And the case of Stockholm was kind of a good example. In my country, Milan, it's not very clear if this is working or not. I think it's because they don't do this in a systematic way. Sometimes this congestion pricing works, sometimes not. It's not very clear. In Milan, they have a problem with pollution. So sometimes the level of ozone and particles is high, and it's dangerous for the health of the people. So that's why they impose congestion pricing sometimes. It's mainly about pollution. But this study, I did the survey in Brussels in 2002. So I was in charge of a main data collection effort. This was million of euros project. So they wanted me to collect data, behavioral data. This is a stated preference. And they were analyzing different policies. So the data collection was very difficult because we had 4 options. So the stated preference included car with delayed departure time, because in Europe, as I said, working schedules are becoming more and more flexible. You can choose what time you are in the office. For example, you can arrive at 10, at 11, you can work half day. Or the use of public transportation, or the use of high occupancy vehicle lane. This was not real. They were just testing. They wanted to include this into the 4-step model and test policy. So we had a number of exogenous variables. We had 18 exogenous variables, of which I estimated 7 random coefficients. I had quite a lot of observation belonging to 900 individuals. So this was a huge effort. I didn't sleep for weeks when I was working on that. All right, so, and I've been using this data for a while now. And we tested all this distribution, right? So what we did, we said, well, let's try all this distribution of this data set and see what is the impact on willingness to pay. That was what the final objective of this study, right? We wanted to calculate willingness to pay. So what we did, we had 6 combination of, and in particular, we were analyzing time and cost. So we had the time and cost normally distributed and cost constant, time and cost normally distributed, time log normally distributed and cost constant, time and cost log normally, and then we had the B-spline on time and on time and cost. So we had 7 coefficients estimated, so I was right. So in order to have these 5 percentile, you need to estimate 7 coefficients for each of the random parameters. So it means that from 2 coefficients, you go to 7. This is the time normal, time and cost normal. So you see that there is an improvement. This is individual log likelihood. That's why it's so low. You need to multiply this number by the number of individuals. Log normal was worse than normal. Time and cost log normal again was not that good, but you see that the B-spline was always gave always better results. These were the distribution. What happens is that, so these are the negative values. So this is the spline. This is for travel time. The problem is, so this is the log normal. You see it's always negative. The problem is that the spline are very difficult to identify at the extreme of the distribution. You need a lot of information, and that's where you have very few information, because these are the people who have very low travel time coefficient or very high. So these are kind of the outliers. So you see that, so I had 2 components for travel time. I had congested travel time and free flow travel time. Although one of the results of this, so we were interested in having free flow travel time estimated and congested travel time estimated. You know why? You know why? Because this goes in the 4-step model, and when you run the assignment, you run for free flow condition and for congested condition, right? You have 2 runs of assignment. That's why we needed 2 values for the travel time. But you see that this is Brussels, and you see that there is not much difference. And my explanation was that the ring is congested all the time. So this was done by a different time of day. We said, well, for some time of day, there is no congestion, but in fact, these are always congested. Brussels is an exception in the European. Brussels is like the United States, because people like to have huge houses outside the city center, and they commute by car into the city center. So, and they use the ring. So it's actually, from the switch from Brussels to Washington, to me was, from the transportation point of view, was the same. But also what I want you to see, so look at the 50%, at the median, right? The problem is that depending on what you adopt, you have a very different value of the willingness to pay. And the question is, which one is the good one? Now, if I look at this, if I look at these numbers, these are euros per hour. So if I look at these numbers, from my experience, I expected to find something between 12 and 15. So I will say that this is a good number. This is not good. It means that there is something wrong in the cost estimation, and especially when I make the cost random. This is good. But this is not good again. So there is something that is going wrong when I make the costs normally randomly distributed. So by looking at these results, I will say to one of my students, just estimate the time randomly distributed. Don't estimate the cost randomly distributed. And again, I will say that this and this number are the number that I was kind of expecting. Also, the distribution is quite reasonable. You see, from about 5 euros to 26 euros, and from about 7 to 26. I will say that these are the numbers that I would have expected. For free flow, a little bit lower, but not much. And again, kind of similar distribution. That's all. So this is a clear case in which normal was working okay. Log normal was working, log normal was not that good, and B-spline was a little bit better than normal. But you know, the fact of estimating this non-parametric distribution helped us to identify which one of the parametric distribution was the right one. Truncated gave similar results, but the values for value of time were a little bit higher. So I want to just truncate this distribution. All right. I want to say a little bit just on this application in finance, then we have 5 minutes break, and then I have another example. Yes?
I'm a little bit confused about the result, because when we are taught to compare models, we are always compare width of the indexes. And your results show the B-spline models are better. But after you check the value of time, then you say, okay, the model is not good. So it kind of confused me about.
Yeah. Well, the trouble in this model is just goodness of fit.
Yeah.
An index that the model is good or not. If you look at the goodness of fit, the B-spline, it's always better, but it's also because you estimate more coefficient, yeah. Right? Yes. And the gain, in reality, it's if you multiply by the number of people, you get quite a significant gain, but you also need to see these numbers. So it's kind of both. But the log likelihood is indicating that the long normal is not doing well. And you can see that also from the values. So this is an indication. And I think the log likelihood is also saying that there is not much difference between the normal and the B-spline, and this is also confirmed by the results. So I will say that for this example, the numbers are consistent in the sense that this is clearly indicated that the log normal is not doing well in fit and in value of time estimation. If I read this, I will say that there is not much difference between normal and B-spline. And this is also confirmed by the values of the value of time. But it's not always like this, because sometimes you can get very good fit and then a not very good value for the value of time. And you see from this how difficult it is well, the idea of mixed logit is very appealing. It's a very interesting mathematical problem. But then in practice, deciding about all this value, obtaining all this value is quite a lot of work. And I think that's one of the reasons you don't see many of this applied in practice. I hope that the new generation will see this applied in practice. But just few consultancies that I know are working on this.
So it we see the result on the last model, would you consider to relocate your NOS more closer to the central point, 50%? I mean, not equally spaced NOS, but you
Yes.
relocate. You improve the...
Yeah, but at the end you want a distribution.
Yeah.
So at the end you will always have this kind of problem. Still, yes. You can increase the precision of the estimation of your distribution, but distribution is this one, is the same. You can increase, yes. You can have 25, you can have 40 and 60. You can have this. This is the beauty of the B-spline. You can refine. Once you decide, for example, let's say that you like this result. Then you go back and you say, well, let's try to have a finer description of this random variable. And then you go up to 40, 60, and so on. You can have even 90% estimated, 10% estimated, because you start to really separate the outliers from the rest of the distribution. Yes?
I want to know, how did you determine the distribution, this 6 distribution? Was there any rule?
Well, the 6 distribution is just because we wanted to compare. When you start to estimate a mixed logit, you always start from the normal, because it's the easiest to estimate. It's kind of the base of your estimation. So this was kind of a must. You start from the normal. Then, given that we were getting about 20% of the population with the positive value of the travel time, we said, well, maybe let's try a log normal and impose a sign to the distribution. But, well, in this,
Is there any method or any approach to...
It's just trial.
The data?
No, but what we are claiming is that if you estimate a non-parametric, you start to get an idea of what is the distribution. So this confirmed that normal was maybe a good approach.
Then try.
Yeah, you try and you see how it looks like, and then, yeah. I just want to show you some results before we have a 5-minute break. I did an application. I was working with people in economics, and they had a data set from Japan on foreign exchange market. So they see the exchange rate of the, what is in Japan? What is the yuan? So, and they decide, so there is a big man, the central bankers decide to intervene in the market, making a public intervention, so saying clearly, I'm devaluating my money, or have a secret intervention that is detected by the market, or have a secret intervention that is not detected by the market. For example, sometimes they make just small adjustment. If you don't declare them, the market cannot even perceive that there has been an intervention. So they don't know the intervention. So these people, they wanted to model this with discrete choice models. So we had 4 choices, and we had the model estimated. So these are the variables. So I just got this data set from them. So these are the variables. It's just to show you that this has application also in other fields, not just transportation. I said, well, let's try to make the amount of the amount invested in daily intervention as a random variable, right? So I said, let's try to create this amount, and you see that they expected the amount to be a positive, to have a positive coefficient, because if what they said, I don't know anything about finance, but what they said is that the bigger the amount, the bigger this amount is known by the people, right? For small amount, the market doesn't even understand that there has been an intervention. So I estimate a mixed logit with normal, and look what I had. I had 50% of the coefficient that was negative and 50 that was positive. So this was clearly wrong because the coefficient was supposed to be positive. But then I estimated a B-spline, and you see that the B-spline was able to recover that for 70% of the intervention, the amount was 0. And just 30% of the time, it was positive and very large. So this was one of the cases in which really applying the B-spline gave me an idea that there was a big mass at 0. Unfortunately, it was not that in transportation, but for this example, it was very clear. So I think this was a very successful application because clearly the fact that I had a non-parametric there gave me the possibility to understand that there was a huge mass at 0. And it's impossible to recover this from the normal because the normal was saying 50-50. So this is a second application that I have on Mixed Logit, always on Moby Drive. And this time, the application is error component. So you see how I estimate the Mixed Logit with error component specification in the case of an activity type choice and scheduling problem. So you know now that the transportation people are switching from 4-step model to activity-based model. And so determining which type of activity we do and at what time of the day is a very important component of all these activity-based models. So there has been a lot of research on that. And the other problem about activity-based models is that once you start to model activity, you start to realize that there is dynamics in travel behavior because the activity you do on different time, on different day of week are different, right? And the activity that you do at different time of the day are different to study. And again, this is based on the Moby Drive, so it's based on a 6-week travel diary. The other thing is that I wanted to account for past history of activity and past choices into the choice of the activities. So I wanted to know, for example, if I did an activity yesterday, am I going to do the same activity today? So there are a lot of lagged variables in that model. And I took advantage of the fact that Mixed Logit can account for panel structure and lagged variables at the same time without changing the structure of the model. So you see the advantage of using Mixed Logit over the probit. Here you see that I specify Mixed Logit. So I specified Mixed Logit with random component, with error component. So I'm taking account for correlation across alternatives and for state dependency. So I'm using number 2 and number 3 on my specification, right? So error component to take account of correlation and state dependency with the sequence of choice specified inside the integral. Well, my claim was that I was contributing to the evolution of the demand model into a kind of dynamic activity-based framework, because for now, all the activity-based models are still developed for one day of the week, right? All these models developed by Eric Miller, Chandra Bhatt, they have activity generation and scheduling, but just for one day of the week. So a little bit of literature on that. So who is working on, so here you see the combination of 3 ideas. One is activity-based models. Another one is day-to-day variability, and the other one is dynamic models. So activity-based models are have been developed and still are under development, and they have been able to transfer this into practice. You know, there are a number of activity-based models developed in the United States, you know, New York, San Francisco, Oregon, and so on. Now Virginia wants to do an activity-based model, so it's something that really, it's not just research, but is transferred into practice. So there are some nice examples. Bowman and Benakiva, they kind of proposed an activity-based model based on discrete choice models. Nagel and Reichert, this is more simulation-based. It's not really discrete choice models, but it's simulation-based. But has developed a very comprehensive activity-based models that was called CHAMDAP, and now I think he changed the name. but he has a number of advanced discrete choice models there. You have all this activity allocation amongst household. He has discrete continuous framework implemented. So it's a very interesting model. Arendse and Timmermans, they proposed also activity-based models, but their models are more, originally they were models, rule-based models, and now it's a kind of mixture between rule-based models and discrete choice models. But in the beginning, they kind of refused the idea of using discrete choice model because they said that the decisions are not made on a rational way, and they did not accept the rationality hypothesis that is behind discrete choice modeling. So they developed everything in a rule-based framework, although now you see many of these components developed in discrete choice models. And Pendiala, he has a model, the famous FAMOS model developed for Florida. So you see that there is a lot of interest. Eric Miller has another model based on simulation and so on. But there is, in transportation, there has been, especially in the early 90s, there was a lot of interest in studying day-to-day variability in travel behavior. And the first one who started to propose to study day-to-day variability were these researchers in Oxford. There was a very good research group there. And Jones and Clark, they encouraged people to collect multi-day travel survey. And not by chance, Kai Sausen was one of the students. So really, they started to think that day-to-day variability was important. And Eric Pass, who was a student of Koppelman, he also has a number of papers on long-term and short-term variability in travel behavior. And there are also issues related to the fact that how long should be this travel diary? Is 2 days enough? Is 1 day of the week and 1 day of the weekend enough? Is 1 week enough? Are 2 weeks enough? Are 6 weeks enough? So there is all kind of debate going on about this, but also, and you will see, I started from this when I started with the idea of dynamic models. So in transportation, there has been an attempt to take into account dynamics in travel behavior, and there is a very important, there is a very interesting paper from Hirsche Ben Akiva, and they estimated a model for shopping activity behavior having a 1-week travel survey diary, in which they account for past behavior when making a decision about shopping activity. There is the famous paper by Mamasani and Jial Chang about the dynamics of departure time of urban commute in a series of simulation experiments. I think they made, this was the first attempt with stated preference and study day-to-day variability, and this is a highly cited paper. And there are a number of dynamic models for car ownership, because clearly that car ownership is a dynamic process, and you will see that's where I started with my dynamic models. This is one of my early attempts to model dynamics in travel behavior. All right, again, the same. So here, I'm not dealing with mode choice. Here I'm dealing with activity choice, so which kind of activity and at what time of day, right? So this is completely different kind of choices. So again, the framework is similar. I'm divided the data in working day and non-working day. The work day are characterized by morning commute and evening commute. So this is from home to work. Yeah, this flash should be, it's from home to work. This is from work to home. And this is a morning tour. It's all the tour. So it's a these are all tours, right? That start at home and ends at home. So I have the commute, right? But the commute I want to know more, because commuting is very important. It's very likely that I have also secondary activity during the commute time. So I divided them into 2 legs. Then I have a tour before work. And remember, I don't have many people doing activities before the commute. And I have an evening tour. The same here, non-working day, I have a principal activity. So out leg, going out and return home. And then I have what happens before that and what happens at the evening. You can also have more of this. For example, you can have multiple tours after the commute, right? For example, you go back home from work, then you go out for shopping, you go back home, and then you go out for restaurant. You can have multiple of these tours. So look at how rich is the data set, because I have about 5,000 activity episodes. So I have 5,000 of these tours. I have more than 3,000 daily schedule, so it means more than 3,000 of this altogether. I have 773 weekly schedule complete, and I have about 144 individual schedule. So this is a very rich data set, and this is the way they are constructing by activity. Right now in state, remember that what you have seen before here, these were modes. Here I have activity. So it's when I'm doing shopping, when I have leisure activity, when I am doing personal business, pick up, drop off, no extra activity, and home for lunch. So these are people going back home for lunch. So let's have a look at these numbers. You see that if I work, it's very likely that I do shopping even on the way from home to work. This is even in commute, it's the return leg home, right? Or after work. You have very big numbers here. Leisure the same. It's very likely that I go out with friends or with my partner at night after work. Let's see here, while if I don't work, all my activities are on this principal tour. Right? I have big numbers here. I do something after, but not much. But I also do something before. I have some people, they go back home for lunch. This is the only work-based tour that I count here. So these are people who are leaving work, going out for lunch, and coming back to work. So you see that I have almost 5,000 of this activity episodes. So this is Mixed Logit with error component. So this is the specification. You see the same specification in train. So these are constant. These are my mu. These are the error component. And this is the logic component of the error. And you see that I also have a panel effect because I have NJT. So I have a sequence of choices. This is the way I specify the likelihood inside the integral. Is a sequence of choice across the time period under analysis. Now, however, now I'm analyzing different correlation patterns because here I can deal with correlation across day, across weeks, and across individuals. So what happens is that in a first attempt, I have just a single activity episode without correlation. In a second attempt, in this sequence, I have all the activity in a day. In the second one, I have all the activity in a week. And on the third one, I have all the activity for the individual, right? So T varies from being 1 to be all the activities in a day, in a week, and in per individual. They are separate models, yes. So this is about the correlation. Now let's look at why I need an error component structure. So this is the choice tree. And in reality, what I wanted to know is which kind of activity I do and when this activity happens. So I have shopping, leisure, personal business, pick-up, drop-off activity, and they can happen in the morning commute, in the evening commute, and evening tour. Always, right? And then I can just do work, or I can go home for lunch. So these are my choices. So these are the activities, and this is when they happen. So I need the error component because these activities are all shoppings, right? So it's like a nest. So I have a common error component for the shopping activity in the morning commute, in the evening commute, and the evening tour. So it's kind of a nest. I'm reproducing a nest with a mixed logit with error component and panel data. And the same, I have this for working day and non-working day.
Do you have any reason why you don't use switch the labels?
Yeah, no, I should have tried, but I haven't done this in this paper. Yeah, it can be which one comes first. Yeah, the difference, it's like first mode or destination, or first destination and mode, yes. No, I have not done this. Okay, so this is the list of independent variables that I have constructed, and I have kind of variables that refers to the day, to the week, and to the 6 weeks. However, I want to point out that there are some limitations here. First of all, for example, you see that activity duration, time budget, especially activity duration, this is considered like an exogenous variables. In reality, if you want to do this correctly, you need to do discrete continuous. You need to allocate time instead of having this as an independent variable. It should be a dependent variable here. But you know, having a discrete continuous with error component and panel, it was too much for that time. So I had this as an independent variable in my. Then I had the time budget, which is the 24 hours minus all the time that you have already consumed by staying at home or by traveling. Then I had available time before work. This was kind of trying to understand the scheduling constraints for work. Available time after work, right? So this was also taking into account the fact that the shops in Karlsruhe, they close down at 6. So if you want to do shopping activity, you have a limited time between the time that you leave work and the time the shops are open. So I had a high week episode, and this was a dummy variable, which is one for the week considered. It's if the number of activity for a specific purpose is greater than 2. It means that you are going to shop more than twice a week. You are going to eat out more than twice a week. And I got this variable from Hirsch and Menakiva, and I decided to use them. Then I also had a kind of past history variable, and this is the number of days between the day considered and the day when the same activity was undertaken. So if a long time exists, so if you did shopping a long time ago, probably you needed to go to shopping again. So this was kind of, and then the number of days that you stayed at home with doing nothing in the period considered. Okay, I would like to say that there are two problems in this model. Although it's a quite complicated model, there are two problems. One is this activity duration that should be continuous and should be independent variables. And the other one is the starting value. Because I started to count this from day 0, but this is not true, right? One way you can overcome this is lose 1 week and kind of start from week 2. I could have done this, but I didn't do it. So there is a problem also with starting value here. I had a level of service variable, and this is to make this under one activity-based framework, because I needed to consider if you are going to a place, you are traveling to that place, so you have a choice both of destination and mode choice, right? So I calculated a mode choice model here. And I calculated the log sum from a quite simple mode choice, and I accounted for this log sum when calculating the accessibility of this activity. So the log sum is kind of accessibility of this activity. How much time and cost is for me reaching these places for these activities. So it's an activity and scheduling problem, but it kind of contains also mode and destination choice model. It's kind of externally done, but it's there. And then I have all kind of socio-demographic variables in this model. Okay, so this is the estimation. So you see activity duration, time budget, available time before work, available time post-work, high last time, etc. I had the logit here estimated. Then I have the error component. And you see that there is a significant improvement when you consider error component because there is indeed correlation across these alternatives. There is not much, let's see, I can barely read this. So there is 9, so this is, there is actually, this is better, right? Yeah. So my claim was that by the fact that accounting for all this deterministic way to account for past history did not improve much the estimation of mixed logit accounting for correlation across different activities. So it means that all these activities that I'm making in the day are different. And so there is not much correlation amongst them, which makes quite sense, right? Then there is an improvement. No, still not improvement during the week, but there is an improvement here. But I want to show you this. So this was with all the variable, right? Now let's see at this, which is just the log likelihood with the set of variables. So consider just the socioeconomic variable, right? This is the way we calibrate always this, without accounting for history. So what happens is that this is for logit, and this is the value of the rho squared. So in this case, when I'm not accounting for past history, the mixed with error component is better. This is okay, this is much better, and this is much better. Okay, so because it's kind of, I'm accounting as random something that I'm not capturing with variables. Now, if I have day behavioral variables, I have quite a significant improvement here. This is better, and this is better. When I have weak behavioral variables, I'm starting to get stable or worse, right? So I'm accounting as I'm accounting all this variability in a deterministic way instead than in a random way. And here I'm doing a little bit better when I put the long-term behavioral variables. So these were the results, these were the application. So you see that in application I'm doing quite well, although the problem is very complicated. So you can see the blue is the forecast and the red is real. So I'm reproducing the choices quite well, right? There is not much difference between forecast and real data. So I was doing well in application, and that you see that I can do this by day of the week. So I can reproduce activities and scheduling by day of the week. So I can apply this to different day of the week. So this is Monday, Tuesday, and this is the weekend. You see the weekend is totally different. I have one model, but still I can do quite well. I can also do this by week. So this is the application by week. This is week 1, week 2. And you can do that for all the 6 weeks. So what I was concluding here is that the socio-demographic variables that are the ones who are commonly used to determine the activity in reality are not those who determine the activity type and the scheduling type. So here was the history that was much superior to the socio-demographic variables. And this was a nice application of mixed logit with error component and panel data.
What time you need to calculate?
Oh, it took me a long time. It took me a year. It took me a year because organizing all the data and estimating all this model, it took me a year. The year before I moved to Maryland, when I had the time. But you know, it's a year of a student. It was a nice paper published. Yeah. No, it takes a long time because here you are combining many difficulties. The data set, all these activities, all this scheduling, and then the model to estimate, and you have 5,000 observation. Estimating a mixed logit with 5,000 observation, it takes a long time. And you know, look at how many runs I had here. I had a number of runs.
So you say the raw square is the number below the...
It's the raw square, yes. The adjusted raw square. So you see that I start very low, but the problem is that I have many, many alternatives. So the problem is quite difficult. So you see, this is another case in which you have a very low raw squared, but look in the application. The application is very good. So this is another case in which low raw squared doesn't mean that it's a bad model. There are some discrepancies in shopping because we were not sure when the shopping were open or not in the weekends, because sometimes they are open during the weekend, sometimes not. So the availability here was kind of strange. That's why we have some of these discrepancies. But overall, we can capture the activities also during the weekend, although we have just one model.
Do you have any suggestion about sample size?
For this?
To develop such a complicated model?
5,000 is a good, no. Well, in my, well, this was 5,000 observation, and I think in this case you need it because you need to calculate all these variables. If you don't have a period of observation long enough, you cannot even calculate these variables. But this was also important for the guy who made that survey because many people were saying, but what are you doing with just 160 households and 360 individuals? It's not good enough. But if he was able to say, well, you see how many activities and how rich is the data set. And so it's true that I have 5,000 observations, but these are just 360 individuals. It's not much at the end.
So the number of individuals is more important?
The number of observations is, in this case, yes, because you get a variety of activities and a variety of scheduling. But if you see the mode choice, there is a lot of repetition because mode choice is very repetitive. So for mode choice, maybe this is not adapted. You need a long travel survey for activity and scheduling, but not for mode choice. For mode choice, for example, maybe 1 day or 2 days is good enough. In the case you have stated preference, also there I should not say, but I also have some magic number. So when you collect stated preference, say with 9 responses per individual, I would say that starting from 250 individuals, you start to have good model estimated. The ideal is to have between 400 and 500. But if you have 200, 250, you start to have good models. The one I had in Brussels, I was very lucky. I had 900 respondents, but this was a huge study, and usually you don't have so many. We had the police collecting this data, so they stopped the car on the highway. We were on the newspapers everywhere, so it's kind of, as a researcher, you never get access to this kind of data. After this Moby Drive, also Belgium collected a 1 week travel survey, which is available. Nobody has used it. In the US, we don't have this kind of study. We don't have any of this panel data available. That's why my research is completely different now. So Europe was more into this kind of study. And
have you ever tried to develop the individual level models? I considered only 2 weeks, 3 weeks.
No, I have not tried, but it can be, yeah, it can be done. Although again, when you do this panel, at the end you don't estimate any extra coefficient. It's just a matter of fitting. So the interpretation that you can do out of this, I don't know if I can even conclude that 6 weeks is too large or too small. It's difficult to say. I got good results, but what is the behavioral interpretation? I don't know.
How many events of log latitude code?
You need to do a log latitude ratio test. So you do the well, in this case, in this case, given that it's always the same data set and it's always the same number of attributes, each improvement is good enough. So if you improve even a little bit, this second model is better. But when you work with with the same data set, a different number of coefficients, then you need to do the likelihood ratio test accounted for the degree of freedom. So you calculate minus 2 times the difference in log likelihood, and you compare this with the chi-squared critical value for this degree of freedom, for the difference in the number of coefficients. So here you can compare directly the rho squared. There is no need for log likelihood ratio test, because it's the same model, it's the same, there are the same observation and so on.
You use the mixed logic to forecast
Yes.
the choice probability. So you need a simulation.
You need a simulation. You need a simulation again. You need a simulation, and also what I have another paper about application of mixed logit. There are not many papers on the application of mixed logit. I don't have the results here, but from my experience, mixed logit does not do very well in application. In all my studies, logit does better than mixed logit in application. I have a number of evidence, but I don't know why. If it is the simulation, the problem, if it is that, you know, in logit, when you have a complete set of alternative specific constants, you are sure that you reproduce the market. This is not true in mixed logit. So I have a number of, I've also published a paper on that. We did a paper with Elisabetta Kerki on that, and we showed that even on simulated data, mixed logit does always worse than logit in application. But I haven't seen any other study, so I don't know, Train, what he thinks about this. But we don't understand why this. I don't have an answer. I don't know why is this. If it is the fact that we are simulating, I don't know. One reason could be that you introduce additional error there. In reality, when you estimate a mixed logit, you fit everything you don't know into an error, right? It's into an additional random error. And maybe this random error is perturbing the ability to reproduce the choices. Maybe this is one explanation, but I'm not sure.
So when you say beta, what do you mean? Focus?
Yeah, when you do the forecasting with mixed logit, although the fitting is better in the application, when you try to reproduce the choices in out of a sample application, it does not do well.
So normally we use the 50%, the median value would be because the output is also distribution, right?
No, we simulate. We draw from when you apply, you draw from the distribution.
Yeah.
So you don't use the median or the mean. You use the entire distribution. So you simulate the choice probability again.
Do we need to simulate several times, take an average?
Yeah, but it's quite stable. If you have enough random draws, this number is quite stable, doesn't change much.
As far as I know, the convergence gives much of chance to draw.
It's Monte Carlo simulation.
Yeah, so the convergence still depends, right?
The convergence still depends on how many draws you have, and but after, for example, 1,000 Monte Carlo draws or 2,000, it's quite stable. Yes, you start to see that the log likelihood doesn't change much, and the coefficient, they don't change much. And the reason for that is, as I said yesterday, it's that at the end, this mixed logit, the function is quite flat. So even if you move around this region, you don't improve much the log likelihood, and you don't improve much the coefficient. And actually, all these results are done in our fantastic software called Hamlet, and there we have trust region, and we calculated the error that we make on the log likelihood, and we calculated the bias on the coefficient. So we stop when we are sure that by making other iteration, you are not improving much the error, and so the error on the log likelihood is less than the improvement that you are making by adding more iteration. So I'm quite sure that we are reaching the maximum and that these numbers can be trusted. Yeah, I never get the case that by changing the seed or by changing the number of Monte Carlo draws, my results changes completely. You are not sure that you are at the maximum, but you are close enough to the maximum. In my experience, it's difficult up to a point to improve, but you get to a maximum. It's I won't say that this is my main problem. The problem is that this is slow, that it's very slow, and that when your model is complicated, some of the software, like the software of CanTrain, they just blow out. It's a nightmare to estimate this. Other question, other possible application that I don't see. We are now working on a paper, but I don't have the slide yet, on about the variability of travel time across days. So that's what we are going to send to TRB with my friend Elisabetta. What else can I say?
Is it possible to specify the beta parameter as a function of variable? Not just
I think is what Chandra Bhatt does. So he says that I don't know. This beta is a function of certain the variance of this, in particular, the variance of this beta is function of certain parameters. So it's certainly possible. So he can get some of the deterministic information in that. Yeah. So he does this. There is a paper of '98 in which he does this. 10 more minutes. I have the slides for tomorrow, but it's Mixed Logit, but it's totally different stuff. So maybe it's better to start fresh mind tomorrow.
So what's your expectation about the trend of the development of? Because like this, the last TRB, there was 3 sessions about discrete choice model. The first session is discrete choice model. Second session is advanced choice model. The third session is more advanced choice model.
What maybe I did not attend that session. So what was there? Because now
the model becomes more complicated.
Oh, yes. The trend is this. So the trend, at least from what I saw last year at IATBR, there were not many mixed logit anymore. We say that this is too much. Although I think it's instructive in the sense that you need to know what is mixed logit. It's kind of, you cannot work on discrete choice modeling now without knowing mixed logit, because even if you don't work, you don't want to produce research on that, you need to know them. That's why I teach this mixed logit intensively to my students. They need to know it. The trend is that you build your own model every time. So the trend is that, first of all, you forget about commercial software. You need to be able to implement your own model. There are also 2 different kind of pattern of research. One is try to understand from the data, so the behavioral side, and not just the mathematical side. And the other is even more complicated model. I don't know what there were in this TRB session, but what I'm seeing now, it's a lot of this discrete continuous, latent classes, latent variables. I haven't seen much of mixed logit. And also not many people doing GV anymore. GV is kind of, we have forgotten what GV is. Some people, they are going back to Probit, trying to understand if part of what we do in mixed logit can be done with Probit, including myself, although I realize that the estimation of this Probit, in my opinion, is difficult. So now what I'm doing is this discrete continuous, and you will see on Friday I'm doing a lot of dynamic discrete choice modeling in the dynamic sense. And I think this is new, nobody's doing it for now. I hope that. And then there is a lot of research on applying this to activity-based model, residential location choice models. So it's kind of the application, finding. So I think the future is finding the right model for your application. So it's not that you apply always the same model, but each problem needs a custom-made model, kind of model. And also all this joint decision, activity allocation, deciding the kind of tour and at what time and how long is the activity, all these joint decisions are now also very popular.
So any research on simultaneous decision? Simultaneous plan?
Yes, yeah, a lot of this. You will see more and more on this, I think. Although the problem is always the same. The people who have the software are doing this, but the other people are kind of left behind. There is a problem in transportation of software. So why Mixed Logit was so popular? Because Ken Train made the software available on his website. So the software was readily available. Once you understand how it worked, you go there, you download the software, and you run it. But for example, if you want to do this with the Chandrabat also has software, but if you open it, in my experience, it's very difficult to understand what he's doing. And it's very difficult to make his software running and reproduce his results. So, and even myself, we have produced many software, but always it's kind of in a rush, it's not well documented. So I have, for example, a good software for Mixed Logit, nobody uses it. I have a good software for discrete continuous and nobody knows it. We have software for dynamic discrete choice models, but it was done in a rush by a student of mine that left, and nobody can use it. So organizing this software, it's difficult. It's time consuming, and you want to publish instead of organizing the software. So this is another problem that we face. It took us 2 years to do this discrete continuous, so it's really a shame that nobody is able to use the software. So I hope we will become better on this, more organized. Yeah, this was the success of Ken Train. So he made available the book and the software, so we were able to understand what he was doing and how to use the software. That's why this was so popular. I think this is the only reason why it was so popular. Huh?
To write your own blog. Your blog.
Sorry?
Your personal website to.
Yeah. I don't even have a website. So yeah. So yeah, we should do this in a more systematic way. So we should, but we are not at that stage yet.